Okay, so the vertical lift contactor, just like I showed in the video, it does the diagram fits or the circuit, electromagnetic circuit fit, right? So just like we had before, you have a DC voltage, all right? You have a resistor and that going into a coil, right? The center piece. And from the coil, just using your right hand, remember your right hand will give you the direction of the flux, right? So due to the flux, if you use your right hand, you round it around, so the current going in this direction. So it will go so, and so. So therefore, your fingers pointing to the right and your thumb will point up. So your flux going up and the diagram have it correct. All right. So when that flux is generated and it goes up, at this point here, it splits to go to the left and to the right. Yeah. So whenever flux is generated here, half of it goes in this direction and half of it goes in the next direction. Right. If you're asking like why isn't it odd-sided? Like if this side had a different shape than this side, it'll be weird. Is what will happen is this piece here will generate like let me say using simple numbers, let me say generate a force of 4 newtons, right? And this side generate a force of 3 newtons. You will agree that when you lift it up, it will lift up like at an angle and it will be weird, so the thing will fall over. Yeah, in simple terms, remember like a magnet, it's pulling. Yeah. So this piece, so what will happen is you want this, and this to pull the armature up at the same rate. You don't want to be working faster than the other one because it will come up lopsided. And what will happen is one will contact and then the others will kind of ripple. It will hit at different times. And you don't want that. So in normal operation conditions, the right and left piece, as you see it in the diagram, is always the same size or the same dimensions, right? Or the same cross-sectional area as you normally call it, right? Right, so continuing, so the coil generate the flux. So half of the flux will go here, half of the flux will go here. And just like I showed you in the video, it generates a north pole and a south pole, just like an electromagnet. And it will just pull the armature up. All right, some terminologies. All right, this piece at the bottom here is called the armature. As you notice, this piece is not connected to this. So this piece here is separate from here. It's not connected. Yeah, think of this as on the ground. Yeah, on the ground, and this hanging. So when it generates add a voltage, it will pull this from the ground up to connect. That's like I showed in the video. And it will just be connected. So just remember that. The armature not connected to the main core by default. Right? It could be, but like if you want it to instead of lift up, you want it to like drop, but not rare. So I already see a question like that before. But anyway, so first thing to remember, right? When you're doing calculations with these questions here, because you have an A gap, right? And normally the A gap is large. And just like we did before with magnetic systems, the reluctance of the A gap is extremely large compared to the reluctance of the core itself and the armature. Yeah? So when you're doing these questions, we'll normally state that the reluctance of the armature is negligible. And it really is compared to the reluctance of the A gap. Yeah, remember when you used to calculate the reluctance of the air gap? Them things real big. You probably see it in class too. And when you actually calculate the reluctance of the core, it's small compared to the reluctance of the air gap, right? So for these questions here, the reluctance of the core itself is real negligible. So they won't really give you like the lengths of all these things here. Like where you custom it, they're not gonna give you all that, right? Right? So just remember that. So if you see a question and you say, well, wait now, the calculate R and the no. Right? So what they do give you and what they have to give you is the air gap length. They have to give you that. And they may label it as G, but G is the air gap. They may label it as X or whatever it is. Right? But in this diagram here, X will be the vertical distance it moves. So when you add a voltage, and flux generates and it pulls it. It wants to know the distance that it moves up, right? And that is this x here for the delta x, right? So it will move. Everything is normally measured from the average diameter, right? So it'll move from here up to here. Yeah, but when you're doing the question, just remember, and where you had rather know, as you see the question, you'll see, you only care about this here. That's all you care about. Yeah? That is all you care about. Really. They will ask you to calculate the force. Okay, our equation for that go straight. But that is all you care about, right? Because the reluctance of the core, negligible. So you know the only reluctance really dealing with is the reluctance of the air gap. Because if you can overcome the air gap, you can overcome the reluctance of the core, right? Yeah? So just remember that. Anytime you're dealing with X or whatever, is literally the air gap, right? So remember when I used to get the reluctance, you used to plug in the total length of the core. Yeah, you don't care about that. The length of the ones is the air gap length. And you'll see with the question. All right, so just remember the circuit. All right, secondly, something to remember, and it will help you when you're doing questions, right? In this shape here, right? If I were to calculate the reluctance of this piece, right, compared to this piece here, it will be the same. Why? Because if you look at it, it's literally symmetrical. Seeing that? It's symmetrical. Remember, R is L on mu A. So clearly the length is the same. So from here to here, the length is the same. And the length is the same on this side. The cross-sectional area is the same. Nothing can change. Yeah? So it will be symmetrical. If I was to calculate this piece here, it will be the same as this piece here. That's by looking at the diagram. Right? So therefore, when you're doing the calculations and you're drawing up your equivalent circuit and stuff, if once you calculate the reluctance of this piece here, let's say RA, and if you name this RB, you could comfortably just assume RA is equal to RB because it's symmetrical. You clearly see it's symmetrical. Yeah? So let's remember that. Something cool to remember. Right. Secondly, breaking up the pieces of this, right? Okay, you had to draw equivalent circuits for this. Right, just like I showed you, right? When you're drawing up the lengths of stuff, you have to keep looking at the diagram there, they will tell you if it's up or down. This one is down, right? So when you're calculating your length, just remember you don't really care about all the length. All the length you care about is this. Just remember that. Once you remember that, when you look at a question, the only values that will really give you is the values you need to calculate the cross-sectional area of each piece. That's really all it will give you. So that might give you just this. And if you see this end view piece here, all it's literally telling you is if you look at the vertical lift contactor from the side, that is what it will look like. That is what end view is. Yeah, you all do the graphics. That is our end view. Yeah, I looking at it from the side. Yeah, so basically what this will give you is the width. All right, and the front view. So looking at it, if that give me this here and they give me this by that will give me a cross-sectional area. And if they give me this here, this by that will give me a cross-sectional area of this piece here. All right. So that is all you really need to know for this question. Right. That's by the circuit itself. All right. I'll show you all the voltage, get MMF, flux. When the flux generates in the circuit, it will basically just lift this movable part up a certain distance. Yeah. The reluctance of the core is negligible compared to the reluctance of the air gap. So you just assume that the reluctance of the core is negligible and you really just work in the question for the reluctance of the air gap. All right. All right. So equations, right? Quality bad, but smart. This in your notes in the drive, so you can check this out. Right. The first one, the popular one, is this. The force, so basically remember, it's a magnet, right? So the force it needs to pull the movable part a certain distance, right? F is I squared onto dl dx. I will show you what I mean by this when we do the question, right? Just remember is a dl dx. So F is equal to I squared onto dl dx, right? And the second popular one, or less popular, is F is equal to phi squared onto the r dx, right? So when I do the question, you'll see what this is, right? So just remember these two equations, right? Make sure you remember it. Because once you know the equation and I show you how to do the question, it's easy maths. Right? So let's remember those equations, right? Right. So without further ado, the best way to understand something is by doing a question, right? So I run through a question quick. Well, two questions, right? So I read it. Right. So the electromagnetic system of a vertical lift contactor shown in figure one has a coil of 400 turns, a resistance of 5, around a center limb, fixed theta, yeah, it fixed. When the switch is closed, the armature is released, it moves to the up position, right? And the air gap in the up position are maintained, so they give you the air gap, right? By wooden spacers, well, yeah, which separate the armature and the stator, okay. The coil is supplied by DC voltage, okay, they give V, and the reluctance of the ferromagnetic coil negligible compared to that of the air gap. That is just exactly what I told you just now. Yeah? So let's remember that and fringing in the air gap is neglected. Yeah. Same thing as I said before, fringing is just the external loss of your flux. Right? Alright, so nice. So that's what the question normally worded, but it's the same thing I asked in the matter, right? So looking at the circuit, all right, so you have a voltage, 20, so there's 5. So from there, you have a current one time, like 4. All right. So remember I said they're not gonna give you all the lengths, right? So they give you the lengths to calculate the cross-sectional area of this piece here and the two end pieces, right? And the wooden space are there, small thing. So it basically just there to maintain a one. So when it pull it up, instead of it hitting the iron and iron, it just parallel space are there. So it wouldn't hit it. Yeah, so it literally maintaining a 1 millimeter air gap length. Right? So that's the diagram there, which is how they normally give you all the diagrams. Right? Nice. So let's start it, right? So let's remember the steps. So the first thing you normally have to do, and the first thing you always need to do is draw equivalent circuit. Always. Always, 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 right? Because you'll get marks for that. So the first thing I'll do is just draw the source, right? So the source is this. I go back to the circuit. So you have a current here that's going in this direction. The flux gonna go up, right? Same thing as before. And we know the flux gonna split to go here and here, right? So there's phi and 2, phi and 2. That's the diagram we did before. All right, so we know these, this is what we care about. The set of reluctance at the core is negligible. They gave you the end view, which is your width, and they gave you these things so you can calculate your area for your both pieces. All right, so they give you a good bit of information. So now you can just continue, right? So if I draw an equivalent circuit out right on this side, so we have the flux generator, right? When it goes up, it had to go up through our resistance. Yeah? So had to go up through this piece here. So this piece in the middle here, remember what I tell you, right? You don't care about the reluctance of the core. You only care about is this, right? The cautious sign up. You don't really care about the whole length. This question is different, right? So the piece we care about is this piece in the middle. Yeah? So now that piece there, we can label that our C for center, right? And then this piece here is our right with the right reluctance. And this here is our left for the left reluctance, right? And clearly you're seeing it symmetrical, right? So therefore, for the center piece, we have our C, yeah? And then on the right, we have our right, and then on the left, we have our left, yeah? And just like I addressed, look, yeah, remember you can't stress that you do not care about the lengths of the code because it's negligible. So the only thing you care about in each piece is the air gap reluctance, the length of that. That is what you care about. Care not about the code. All right? if they were to give you a question with the core which is rare in your circuit itself, you would just have to add in the reluctance of the core material itself. So you'll have to like go from here up. So just like we did with the question from before, it would be the total length minus the length of the air gap. Remember this piece here is the air gap. And then for this piece here, it will go from here to here, then to here, minus the length of the air gap. Then you have the piece at the bottom. So this piece here, go down, come around. So that'll give you two pieces. So you call this one our right C, center, sorry, core, and then this one will be our left C, the left core. Yeah? So it'll just have two resistors here and one here too. Yeah, so but that rate, because it's negligible. If you bring that, you just with it, right? But it's the same idea. That's how they add in the reluctance to the core pieces, right? So nothing. Right? Probably before exam, I'll do a question like that with you. But for now, just understand this. That is the one he does always bring. Right, so there's our length. So we draw the circuit, right? So the next thing that we know is that we know that the reluctance of the left piece is equal to the reluctance of the right piece. Because you can clearly see that it's symmetrical, right? This length, same as this length. So all things considered, they'll have the same reluctance, right? Yeah, so nice. So now we need to write an expression for this reluctance here, right? So we know R is L on mu A, right? So in this case, again, the unit length we care about is the air gap, right? So this mu will turn to mu zero, and this A will be A G, and this L here, you could put it as G, but you can leave it. Just know that this L here is the air gap length. Just remember that. If you want to put X, just to change it up, we could. But just keep that in mind, right? All right, AG, we can calculate AG, right? So AG is this piece here, the cross-sectional area of that piece, because I the air gap for the center piece, right? So that'll be the length, 40, multiplied by the 40 on this side, right? So like 40 by 40. Yeah, so let's keep that in mind, right? So nice. So we have that. So now we can just write an equation for that. So we call it L on mu 0 by 40 by 40 millimeters, right? So we just write it. We're not plugging in any lengths as yet. Because remember the question asks for the force, right? So that's follow through the steps, right? Because is this the DL and DX part of the string, right? That is why you can't plug it in as yet. You gotta work that part first and then plug in where you need. Right, so we calculate R, that is the second thing. So after you draw your equivalent circuit, you gotta just get the resistance. So that one. So we have another resistor value that is R L, which is the same as R. It's supposed to be right. Yeah, left and right. So that is still L. There's the same length. And that will be mu 0 by E. Right. It really matter. Right. So the AR now, if we go back to it, is this is 20 by this. Yeah. So it'll just be equal to L on mu 0 by 20 by 40. Yeah. Nice. So we have the reluctances. So what we need now is to find the total, the RT. Right. And then another thing that real cool is that when you're doing the question, right? If you're looking at this, because it's symmetrical, if you put these two together, you will actually get the centerpiece. Yeah. So what the best way to do now is if you look at the areas, right? This 40 by 40 is 1600, right? And then 40 by 20 is 800. Seeing that? So with this, you could call this one a center. Yeah. And this one here now, we know this is half of the A center, right? But the easier way to write it would just be that this centerpiece is just 2 by the area on the right, and this here just staying as a right. Yeah, you could just do the fractions with, but something to just make it move faster is that the centerpiece is always just twice the two end pieces. Yeah, so that's something cool to remember. So basically, the centerpiece is just twice the area, the side piece, the RL and the R. Yeah, so for this piece here now, we could just leave and write it as it's in a different color. So it'll just be 2 by 20 by 40. Right, and this one here is just, well, 20 by 40. I'll see that. Yeah, so that's something cool. If you don't see it, just do the fraction, right? You'll get the same answer. All right, so we just calculate the reluctance, right? So we had to get RT, yeah, because we're working up to the total R, right? So it will just be the RC plus here RR, because RL and RR is the same thing. So now we will just end up with L on mu 0 by 2 AR. Just keep that in your mind. All right, plus L on mu 0 AR, right? So you just do your little fractions, you combine the denominators, you just end up with 2L on mu 0 by 2 AR, right? Because that will be a common denominator there, right? So this here, this at the bottom, you get 1, and then this at the bottom here, you get the other piece. Yeah? And I does your fractions. So you could probably try it out. So you get RT, right? So the question 70% done, right? Notice we didn't plug in the air gap lengths as yet. We're just working down to get the final equation. Yeah? So now we just do this. So remember the equation that we're using, the default equation that we normally use is this one here, the I squared onto dl dx. That is the one we're using, right? So let me just write that. So F is equal to I squared onto dl dx, right? Right. So we have R. The reason why we calculate R, right, is that we need to differentiate L with respect to X. Because that's what this piece here telling us, right? The equation for L is N squared on R. Yeah, so that is why we needed to calculate this R. Because in order to differentiate L, you need R, and they already give you what N is. So that is why we needed to calculate the equivalent for R to get it, because we needed to plug it into the equation for L. Because then you just differentiate in L with respect to the X. This X here is like the L. That's why I normally like to write it as X, because the equation have it as X. So these pieces here, I have to write them as X, because then I will go here and get confused. Because I have an L on top and I have an L at the bottom. So I write it as X. Yeah, all these as X's, right? But for now, just know, and you should know the L here is just the air gap. The X here is the air gap, right? Anyway, so there you go. So to get L, but we need to get L before we differentiate with respect to L to X, right? So L, we just had RT on top already. This piece here. Yeah. So it would just be, and I think they gave you N as N 400 here. They gave you N as 400, right? So therefore this would just come down to be 400 squared that I N, right? Divided by your RT, which is your 2. All right, an X, right? But that's known as the L. It's the same thing from on top. Divided by mu 0 to AR. Yeah, it's plugging in the values. So now we have everything, so we could just flip this on the next side so it'll make it easier to see. So that's turning into 400 squared by mu 0. Yeah, that's flipping it. Yeah, that's dividing it, right? Let's remove this double division by 2AR all on 2X. Nice. So now after you plug in the RT, we can actually just differentiate this to get the L with respect to dx, right? You differentiate L with respect to x, which is this x here, right? If you're not showing differentiation, what I like to do is just, instead of writing the x in the denominator, write it on top. So we'll just turn to -1. Remember the inversion of it, so we'll just go to -1, right? So now we can differentiate this. So differentiate to bring down the power minus 400 squared mu 0 2 AR, yeah, and over the 2, and I subtract 1 from the power, so this will be -2. Yeah, and then I can rewrite it in a nicer way. So minus 400 squared mu 0 by 2 AR all on x squared. I'll just bring it back. All right, so what I did there, this first piece here, I plug in the RT, which is this piece here. Then I just flip it to make it easier to see. Say that's the 400 squared divided by 2x and mu 0 2r will be 400 squared multiplied by mu 0 2r AR on 2x. All right, and then to differentiate, now if we're working out the differentiation, I just move the x to the -1 on top. You differentiate, you bring on the minus over the thing, and you subtract 1 from the power, and then I bring it back down to the denominator to make it look a little nicer. Well, so 2 here, right? And that is all I did. So that there is your DL with respect to x. Right, that is why we needed to calculate the RT because L is n squared and R. Right? Nice. So now what we could do, we could plug in the values. They will give him mu 0 in the exam, right? So AR is 20 by 40. So after you do that calculation, x here, they gave you what x is, right? 1 millimeter. So that is what, 0.012. Yeah. So you plug in that, convert it to SI units in meters, right? You just plug that in here for the X. You plug in your AR, right? And you will get your DL and DX, right? So now I ain't gonna do that because I already had the answers. You try that. But now just worry about the stuff, right? Okay, I already had the answers. Okay? So now after you do that now, you're going back to here. So you're basically done, right? I squared, man, make it get I because they gave you what the voltage is and they gave you what the resistance is. Yeah? So you can get I, there's I here, right? So 20 divided by 5 is 4, right? So just like that, we have I. So now we just come here now. So 4 squared on 2, right? And then multiply that by 400 squared by mu 0 by the 2. Okay, that's put 40 by 40 and then this. Because 2 by 20 by 40 get it right, that's 40 by 40. Because 20 by 40 is 800 and 2 by that is 1600. Yeah? Right? Divided by 2, 0.001 the x squared. Yeah, we just plug in all the values. And after you do the runaway wrong maths, you should get 1286.8 newtons, right? And that is the answer. So that's a recap. Let's go back to the steps, right? So I'll change the color. Right, so they gave you a vertical contactor question, right? So they gave you the nice circuit here, right? Same steps as I said before, the reluctance of the core, negligible, right? So the only thing you care about is the reluctance of the air gap, right? And they will give you what the air gap length is, okay? So now what are you really doing? First thing you have to do is get RT, right? So that is what, right? So the R center, the center piece here, and you have your left and right. And just remember your left and right will be the same reluctance. So you could just make this assumption when you're drawing it up and just calculate once, right? And then for the area, that's like I say, the center piece is always twice the end pieces. It's supposed to be symmetrical. Otherwise, you'll get a lopsided lift. So one side could be stronger than the next side could be looking kind of weird. Yeah? So there's a comfortable assumption to make, right? And then with the areas, that's like I did here, it's the same thing, a centerpiece, 2 AR in the exam, when you do the question, you can put a side AS if you want to. It don't really matter. Yeah? And when you plug in that together, then you add it up together. R center plus your RR. So this plus that. Right? And you get this value after you combine the two of them together. All right? And then after you do that, I RT. So now when you get RT now, 5. This piece here. Remember, you're trying to get the L and the X. So L is N squared and R. In this case, N squared and RT. You plug in your RT into the equation, right? And if you simplify it, so you're working down to differentiation, right? So you bring the X on top, you differentiate, and they get your answer, right? The L on the X. Right, so now you have the L on the X, you have to get I. You should be able, they did go and give you what I is, where you can calculate it because they give you V and R. V is equal to IR. So I is V and R. Get I, 20 and 5 is 4. And you plug it in. So you have R, I, you have everything you need here. So you plug back in here, well, in this case, the AR. Mu 0 is a constant that will give you in the exam, and this is your X, your air gap. You plug it in and you get your answer. And that is question done. All right? That's all our pieces. And that's how I get the voltage. And it's the same steps that I will go through because the shape will be symmetric. Otherwise, it will look way, it will lift up weight. Right? So let me try. So that is it. All right. So I try the next one. So this one here was a past paper question, I believe. Yeah, this was a past paper question. Right. Just like how the say it here is how they wanted it to answer the question, right? So let's see. Look at the notes on it. Right, nice. So same idea, right? So there's the circuit. I read the question, right? So they said the electromagnetic system, blah, 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 use series. Yeah, we know this, raising it up and down. When the armature is up, it makes contact with the player. Yeah, it establishes as well. Look what they give you there. Air gap lengths. The movement from down to up position takes place when the switch is closed. Right, steady state of 5 amps, right? They give you N, right? The same sentence, the reluctance of the magnetic material in the stator and armature are very small in comparison to the air gap reluctance, just like before. Fringing is neglected. Same idea as before, right? That will be the question, similar, right? And just like before, determine the magnitude of the force acting on the armature when it's in its up position. Remember, when it's in its up position, the force they're using, they have to maintain it at a height, right? Because remember that before you're pulling it up, and to keep it up, you have to supply that force continuously. Okay, if you drop it, they're going to drop it, right? If you play with it, they go kind of fluctuate, right? Nice. So just like before, we only give you the information to calculate your cross-sectional areas, right? Just like before. This is your heights there. Just like before. This question here now is only one half to give you. Yeah, but it's the same idea. All right. So we know we don't care about the reluctance of the core, so we can name this one R center, and we can literally name this one R right. Yeah. And the same idea. So now that they give you right, anyway, so mu 0 will give you any question, right? So our center, we label this X, and that's for that how the question is labeled, right? So we can say X, RC is X on mu 0 by AC. All right, so AC is the area, the centerpiece, which is this piece here, which is 40 by 40. Right, that's like we did before, right? So we know that gonna be 2 RR, right? So I just gonna write that one side because I will win. It's gonna be 2 by the reluctance of the right air gap, right? So let's leave that like that. That's like before. And like calculate what R is. So R is the XL divided by 0. And we know that that's gonna be AR, which is if you go back to it, 20. Oops, I rotate the page. 20 by 40. Right. Hope it didn't get easy. Right? So 20 by 40. Right, remember there's your NV. Okay, so let's write it here. AR is 40 by 20. And the center is here 40 by 40. All right, nice. So we have some information. The second thing we had to get is RT. So that is X is 0 to AR, sorry. plus x mu 0 AR, right? So after you do whatever you had to do there, you should end up with 3x on 2 mu 0 AR, right? After you do the fractions and you combine it. Okay? So yeah, nice. So then now, and you can clearly see that, right? Because there's two, if you bring it outside, it'll be a half plus one, which is 3 and 2. All right, but anyway, so we have our same idea. What's the next thing? Right? The equation f is I squared on 2 dl on dx. All right, same idea. Come down here. L is n squared on r. All right, they gave you what n is. I believe is 400, 600, right? 600. So that'll be 600 squared on 3x on 2 mu 0 AR. You flip it to make it look nicer. So it'd be 600 squared by 2 mu 0 AR, right? All on 3x. Then you carry the x on top, you're trying to differentiate on 3, x to the power minus 1. Then you differentiate, bring down the minus. 600 squared, 2 mu 0 AR on 3. And this will be x to the power minus 2. Right? And then now, you just bring it back at the bottom, right? Because that's how it was before. Yeah? Right, nice. So now, you're plugging it into this, right? So, something I didn't mention before, some nobody have asked, right? So, you see, and this minus here. So, you might be asking, like, well, where the minus going, right? So, remember the height, it started from a deficit, right? So, when you move it up, it can be the negative of what it was. Remember, it can be down by default. So when you're move it up, you're giving it a offset. So it wouldn't be at its neutral point. So therefore, the dl would just equal to minus dx. In this case, the dl is just the length you move, so it would be minus. So what has happened is this minus will cancel, and you just end up with a plus. Right, so that's what has happened. Right. Or if you want to, you could just put the modulus of it. This the force can be that be positive, right? Anyway, so I squared. All right, so 5. Right, they gave you what I is. 5, right? Yeah, well, they give you I is 5, that's one. 5, so sometimes they'll give you what it is. So it'll be 5 squared on 2 by 600 squared. 2, mu 0 is a constant. AR is 20 by 40. Um, over 3x squared. X, what they give you the area first? Most likely is 1. Yep, 1. So 0.001 squared. Right? So when you plug in a calculator, you should end up with 315.93 newtons. Right? And with that said, that is your vertical lift contactor questions. Right? So the same steps. Yeah, that is literal. It's literally the same steps. It doesn't really change. Once you analyze the circuit, you can determine it like this here, or you can bring it like 1/2, but it will be the same idea. All right, so any questions on it? All right. No questions? I think you should have or will be going on this soon. All right, so all right. So that's all I wanted to catch. I know they have